For the rest of your life, you're going to hear statements like these. And if you don't want to be cheated out of money, a healthy planet, or your own health, then you need to be a clever scientific thinker. That means knowing how to interpret data that studies present to see whether a statement is likely true or not. It also means that when you do your own research, you need to know how to present the data you collect. Studies often present their data in the form of graphs. 3 of the most common are bar graphs, line graphs, and best fit line graphs. In what situations are each of these graphs used? Experimenters use bar graphs to represent distinct groups in an experiment. For example, groups A, B, and C could be paper, plastic, and styrofoam cups respectively. It's not like a styrofoam cup is part plastic and a plastic cup is even more plastic. They're just totally different from each other. They are unrelated independent variables. In contrast, if there is one independent variable, an experimenter might consider using a line graph to represent their data. For example, one group used all paper cups in their experiment, a larger cup, a medium cup, and a small cup. Now, they had to connect the lines like this right from one cluster to the other, because they didn't know how much bigger the large one was than the medium one, or how much smaller the small one was than the medium one. So if you don't know the mathematical relationship between each of these groups, line graphs are best. If you do know the mathematical relationship between groups A, B, and C, for example in the 1 cup, 2 cups, 3 cups scenario, then a best fit line graph is the way to go. Because you know how much larger 2 cups are than 1 cup, you can place them at just the right interval on your x-axis, which means that you can then draw an estimated best fit line through all of your data points to generalize a pattern in your data. But you can only do that if you know how much bigger or smaller or more acidic or something like that one group is than another. Each of these graphs has pros and cons. For example, lots of people gravitate towards bar graphs because they're very simple and easy to read. In many experiments, people perform things where one group has some characteristic that another group just simply does not. And in those cases, a bar graph is perfect. However, you can't use a bar graph to make predictions about some new category D, for example. So that's one drawback. With a line graph, you can make an approximate prediction. For example, say you get a cup that's somewhere a little bit bigger than a small, but a little bit smaller than a medium. You might know that the data points are going to fall somewhere between here and here for this next cup. You don't know exactly where, however, so this is an approximate prediction. But line graphs can give you that approximate ability. In other words, you can rank items, though not precisely. Best fit line graphs are useful if you can ensure a mathematical relationship between the groups, which is not always possible in science. However, an advantage is that if you can do that, you can use the best fit line graph to predict what would happen at a different value. For example, you can see that the line is going this way, so if you got a new group that was, say, going to be collected at D right here, you could say, well, the approximate value would be this, and you can predict future values from your best fit line graph. To be sure you understand the differences in applications of these graphs, I'd like you to read 3 different experimental designs and decide which graph would be best. You can pause the screen at each of the following experiments and write a little statement such as, I think that experiment 1 would best be represented with a graph because... Alright, here's experiment 1. How about experiment 2? And lastly, experiment 3.